Hello, I'm Brian Young, and today we're going to do Module 26109, Conductors and Cables. Let's get started. 26109, Conductors and Cables. Successful completion of this module prepares you to do the following. Classify conductors by wire size, insulation, and application. Identify wire sizes, determine conductor ampacities, identify conductor materials, identify conductor insulation, identify fixture wiring, identify cable types and applications, and identify instrumentation control wiring. As an electrician, you select the correct wire or cable for the job. You may also need to pull this wire or cable through conduit runs in order to terminate it. In this module, you'll learn about the conductor types, cable markings, color codes, and ampacity derating. You'll also learn how to install conductors using fish tape and power conduit fishing systems. It says the term conductor is used in two ways: to describe the current carrying portion of a wire or cable, and to describe a wire or cable made of the current carrying part of the outer covering or insulator. Unless noted, this module uses the term conductor to describe the wire assembly that includes the insulation and current carrying portion of the wire. Factors used to identify conductors and wire size, type of insulation, and application. In this section, you'll learn how to use these features to classify conductors. 1.1.0, wire size. Conductor size refers to the cross-sectional area of the current carrying portion of the wire. A conductor's ampacity is affected by the conductor's material and size, insulation, and installation location. Ampacity is described as the maximum current carrying in amps a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Wire sizes are expressed in gauge numbers. The standard system of wire sizes in the United States is the American Wire Gauge System. 1.1.1, American Wire Gauge System. The American Wire Gauge System uses numbers to identify the different sizes of wire and cables. Common American wire gauge wire sizes start at 40, the smallest, and go up to 4/0, the largest. When a 0 is used with wire sizes larger than 1, it is pronounced aught. For example, 4/0 is pronounced as 4/0. The explanation I was given is that the copper wire is pulled over pulling wheels, and those pulling wheels will stretch the wire and make it smaller. So if you pull the wire over one wheel, one pulling wheel, it will end up being a number 1 wire. If you pull it over 2, it'll get smaller. It'll be a number 2 wire. And if you pull it over 3, it'll be a number 3. And we usually, after 3, we use even numbers: 4, 6, 8, 10, 12. So when you're working in the field, you're going to hear people talking about number 12 gauge wire, number 10 gauge wire. 14 gauge is the smallest wire we use for branch circuits in the electrical industry. There are smaller wires. They're used for communication and for telephone and data, but they're not used for branch circuits. So from here, 14 gauge is about the smallest that we'll deal with in the field, on up to what they call aught. And I don't have any good way of explaining what aught is. Using the analogy of pulling it over a pulling wheel, aught means it was not pulled over a pulling wheel, but then that means 2/0 wasn't pulled over 2 wheels. It's kind of a funny system, but they're saying it almost like it's a negative number. It's 1/0, 2/0 is larger than 1/0, 3/0 is larger than 2/0, and 4/0 is the largest wire size for which the American wire gauge sets a number. Anything larger than 4/0, we'll see later on, it's expressed in cross-sectional area in circular mills. When we get to that point, we'll see. It'll talk about circular mill area. So a larger cross-sectional area of the current carrying portion of a conductor allows for a higher amount of current to be carried by the wire. Any wire larger than 4/0 is identified by its area in thousands of circular mills, KC mill. Wire sizes smaller than number 18 are usually solid, but may be stranded in some cases. Wire sizes of number 6 gauge or larger are stranded where installed in conduit, but may be solid when used for grounding and bonding. For wire sizes larger than number 16 gauge, the wire size is marked on the insulation. So you can see a wire, it'll tell you it's a 4 gauge type MTW or THHN. That's the type of insulation that the wire has, or THWN. It's good for 600 volts. They'll put all of that information on the jacket of the conductor. It says for descriptive information on wire size, including the area of a certain wire, the stranding and the DC resistance, refer to NEC Chapter 9, Table 8, Conductor Properties. Let's go ahead and take a look at that now. Here's our 2023 version of the NFPA 70, the National Electrical Code. And, well, we always start in the table of contents, but really there's no reason to start in the table of contents because we know we're going to Chapter 9. We're going to go to the very end of the book, to Chapter 9. What's going on? Why is this not working now? Okay. Here we are in Chapter 9, Table 1 of the National Electrical Code. My PowerPoint was giving me problems for some reason. But this tells us in Table 1 the percent of cross-sectional area of conduit and tubing for conductors and cables, that if we only have one conductor in a conduit, it can take up 53% of that conduit. If we have two conductors, they can only fill that conduit to 31%. If we have over two, and this is usually the case for us electricians because we have a hot, a neutral, and a ground. So when we have over two conductors, we go with a 40% fill. So most of the time you're going to be dealing with a 40% fill. So if we look at Table 4, here's Table 4, dimensions and percent area of conduit and tubing. You'll see over two wires, 40%. This is the cross-sectional area of the conduit. This is 40% of the cross-sectional area in square inches or square millimeters. We're going to use square inches. So a half-inch conduit gives us 0.122 square inches for wire fill. 1 inch gives us 0.346 square inches for conduit fill. And it shows us different types of raceways as well. It starts with electrical metallic tubing, electrical non-metallic tubing, flexible metal conduit, flexible metal conduit, intermediate metal conduit, and it tells us the article that covers that raceway system. 356, liquid tight, flexible, non-metallic conduit. So if we go past these, we're going to get to Table 8. Table 8 is going to give us conductor qualities. Let's see, this is Table 5, which is also a good one to know because you're going to need Table 5 when you're doing conduit fill. Here's Table 8, conductor properties. We were just talking about the American wire gauge number for the wires, and if you look, this tells us the circular mill area of a number 18 wire, 1,620 circular mills, a number 16 wire, 2,580, a number 14, and again, that's the smallest size we use for branch circuits, is 4,110. Number 12 is 6,530. Number 10 is 10,380. And you'll notice when they get to 4-aught, they tell you it has 211,600 circular mils. And then they stop giving us that information. That's because above 4-aught, the name of the conductor is the circular mill area. So a 250 kc mill is 250,000 circular mils, and a 300 kc mill is 300,000 circular mils. It even says that this first column is the size in the American wire gauge or in the kc mill, 1,000 circular mils. Okay. Again, it also gives us the direct current resistance at 75 degrees Celsius. We'll talk about that later. Also, look at the quantity. 1 is a solid conductor and 7 is stranded. So when you're looking, if you're looking for a solid number 10, make sure you use the row that says 1. And that'll give you the properties of a solid number 10 copper conductor. And then as you get to larger sizes, you get to where they're going to be stranded regardless. You don't have a solid number 6, 4, 2, 3, 2, 1. They'll show you the different strands: 37, 61, 91, 127. Also, notice how all of the stranding in these wires, it's always an odd number: 1, 7, 19, 37, 61. We'll talk about that in a moment. We'll see why that is. All right, let's go back to the book. 1.1.2, stranding. Solid conductors are made from one piece of metal. Stranded conductors are made from multiple wires bunched together. While solid wires are somewhat rigid, stranded wire is more flexible and easier to work with. Here's a highlight. Using solid wire sizes larger than number 8 gauge for applications such as pulling in conduit around bends or terminating in pull boxes, disconnect switches, and panels is very difficult. It can also result in damage to the equipment and the wire insulation. So anything larger than a number 10 wire pulled in a conduit, we pull stranded wire. According to NEC Chapter 9, Table 8, wire sizes number 18 through number 2 have 7 strands, while sizes number 1 through 4-aught have 19 strands, and wire sizes between 250 kc mil and 500 kc mil have 37 strands. Again, let's take a look at why it's always an odd number. I'm going to open my Here's my magic writing implement. So if I have one conductor, it's solid. And if I have stranded, the next size up, I'm going to put 6 strands of the same size around that one. So 1 and 6 are 7. So we have 1, we have 7. The next size up, I'm going to put 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll put 12 around those 7, which gives me 19. 7 plus 12 is 19. The next layer will have 18. 19 and 18 is 37. The next layer, I'll put 24. 37 and 24 is 61. So notice how every time I'm putting an even number of strands around the existing strands, but there's always this one strand in the middle that makes them all an odd number. So 1, 6 plus 6 is 7, plus 12 is 19, plus 18 is 37. Does that make sense? Hopefully it does. There. And each time we're adding 6, 12, 18, 24. So the next layer would be plus 30. There. It just keeps building out like that. All right, back to the So here's 7 strands. Here's 19 strands. So 1 plus 6 is 7, plus 12 is 19, plus 18 is 37. And it just keeps getting larger and larger. Aluminum conductors are designed with compact stranding. Compact compressed conductors have strands that are shaped almost like the ice blocks in an igloo. So they're not necessarily hexagonal the way they're drawn here. They're actually drawn, well, take it from me, they're more like the blocks in an igloo. Let me see if I can get back to my drawing here. They'll have 1, and then these 6 will be almost like keystones. And they're shaped this way on purpose to make them compact, so that there's not any air. If you can see all of the air in between all of these strands in a stranded conductor, that doesn't make it function any worse, but it just takes up more room when you have all of these air gaps in between your strands. What they do with compact conductors is they shape those individual conductors in such a way that they will stack up around the existing cable, and they fit very tightly with no air in between them. It makes it a little bit easier to pull into conduit. It doesn't increase the efficiency really to any remarkable extent, but it's just something that they do that makes the wire a little bit easier to work with. Why is wire size a critical factor in a wiring system? Other than load, what other factors may dictate the wire size? What can happen when the wire isn't properly sized for the load? Well, it's all about cooling. It's all about making sure that the wire can dissipate the heat created by the flow of current. So we make sure that there's enough air around the wire to allow it to dissipate heat. We also make sure that we limit the amount of current on a conductor to limit the amount of heat that it produces. We want to make sure that we use a wire size that is oversized rather than undersized. Here, 1.1.3, circular mill. A circular mill is a circle that has a diameter of 1 mil. That's 1,000,000th of an inch. A mil is 1/1000th of an inch. 1,000 circular mil is equal to 1,000 mils. When a wire size is 250 kc mil, cross-sectional area of the current carrying portion of the wire is the same as 250,000 circles having a diameter of 1/1000th of an inch. This may seem to be a rather clumsy way of sizing wire at first. However, the alternative would be to size the wire as a function of its cross-sectional area expressed in square inches. So this is a diagram of a circular mill. It's magnified because it's actually 1/1000th of an inch. If I had 999 more of these and I stacked them side by side, it would only take up an inch. It's a circular mill. One point 3.0 conductor material. The most common conductor material is copper. Copper provides excellent conductivity, low resistance, ease of use, and value. The value of a material as an ingredient for wire is determined by several factors, including conductivity, cost, and workability. Electricians selecting a conductor must consider these factors, as well as building plans and specifications. Conductivity 1.3.1. Conductivity is a word that describes the ease with which an electric current travels through a conductor. If a conductor has a low resistance, it has a high conductivity. Silver is one of the best conductors since it has very low resistance and high conductivity. Copper also has high conductivity, and aluminum has good conductivity. The conductivity of aluminum is approximately 2/3 that of copper. Cost 1.3.2. Cost is always a consideration when selecting a material for a job. Given a choice between an expensive wire with very high conductivity and a less expensive wire with high conductivity, which would you choose? So silver has a higher conductivity than copper, but we don't use silver wire in a house because of the expense of the silver. Copper is much cheaper. Electricians typically select a lower cost conductor, even though the material has physical properties that are inferior to more expensive material. For example, it's easy to choose copper as a conductor material instead of silver because silver is very expensive. While it might be a better conductor than copper, silver still isn't worth the extra cost. The choice between copper and aluminum is often more difficult to make. Copper actually is a better conductor than gold. Everybody thinks that gold is the best conductor. It's not. Silver is the best conductor. Silver, then copper, then gold. The reason we like to, in high precision instruments like NASA, they'll gold plate their contacts because gold does not tarnish. That's why they use gold. Out in space, it won't tarnish, so they won't get pitting, they won't get dirty contacts. That won't work. It's a better material, even though it's not as good of a conductor. Cost also depends on availability. When the raw material to manufacture conductors aren't readily available, fewer are made, so fewer are available. In this situation, the cost of the conductors goes up. 1.3.3 Workability. Workability refers to how easy it is to work with a product. Some factors that affect the workability of wire are the weight, flexibility, the need for special or expensive tools, the need for special training. For example, aluminum conductors are lighter than copper of the same size. They're also much more flexible than copper, and in general, are easier to work with. However, terminating aluminum conductors often requires special tools and treatment of termination surfaces with an antioxidant material. Aluminum expands and contracts with heat more than copper. That means that splicing and terminating aluminum conductors often requires a higher degree of training than working with copper wire. Terminating aluminum wire. When terminating aluminum wire, you must always use listed connectors and use an anti-oxidizing compound. Note that some connectors come pre-coated with a compound. If not, you must add it. 1.4.0 Conductor Insulation. The first attempt to insulate wire was made in the early 1800s during the development of the telegraph. This insulation was designed to provide physical protection rather than electrical protection. Electrical insulation was not an important issue because the telegraph operator operated at low voltage direct current. This early form of insulation was a substance composed of tarred hemp or cotton fiber and shellac, and was used primarily for weatherproofing long distance distribution lines to mines, industrial sites, and railroads. Early electrical distribution systems used the knob and tube technique of installing wire. Wire in buildings was pulled between and supported by ceramic knobs that were fixed to the building structure. When it was necessary to pull wire through structural members, it was pulled through ceramic tubes. The structural member was usually wood. So this is what they mean by knob and tube. This is a knob where the wire is held off of the wood member, and this is a tube that runs through a wood member. Knob and tube. As dangerous as this method may seem, there are still older homes that rely on knob and tube wiring that was installed in the early 1900s. In fact, knob and tube wiring was used until 1957 in some areas. Today, bare grounded or neutral conductors are only allowed in the following specific situations: in overhead services, in type SE cable, where used as a service entrance cable. However, when used inside buildings after the first overcurrent protective device, all current carrying conductors, including the ground dead conductor, must be insulated. 1.4.1 Types of insulation for 600 volt to 1000 volt conductors. There are many 600 volt insulated conductors. Each one has its own letter designation, and each is made of material designed for use in a specific environment. For example, type SA uses insulation made from silicon rubber. When rated up to 194 degrees Fahrenheit or 90 degrees Celsius, silicone insulation can be used in dry and damp locations. NEC Table 310.4 lists the application and construction for 600 volt insulated conductors. Based on the notes with NEC Table 310.4.1, conductors in the table are permitted to be rated up to 1000 volts if listed and marked. Thermoplastic insulation. Thermoplastic is a popular and effective insulation material. The following thermoplastics are used as insulators in today's wiring cable: polyvinyl chloride, polyethylene. This is a highlight. It says polyethylene, an excellent weatherproofing material used primarily for insulation of control and communications wiring. It's not used for high voltage conductors, those exceeding 5,000 volts. Cross-linked polyethylene, nylon, Teflon. We use a lot of nylon-coated wires. They're thermoplastic, but then they have a nylon jacket. Primarily used as jacketing material, the THHN building wire has an outer coating of nylon. It makes it easier to pull into the conduit. The nylon makes it a little bit slicker. Thermoset 1.4.3. Although many thermoplastic materials deform when heated, thermoset materials maintain their form when heated. This is a highlight. Thermoset insulation includes RHH, RHW, XHH, XHHW, and SIS. You can think of that R as standing for rubber. That thermoset is kind of a rubberized insulation. Thermoplastic is T. Thermoset is R. And when we get into the table 310.4, we'll see that we have H for heat, and HH for high heat, and W for weather or water. So the letter coding does make some sense. Like if we had a THHN, we'd know that it was a thermoplastic, good for 90 degrees Celsius, high heat, and a nylon outer jacket. Letter coding. Conductor insulation as applied to building wire is letter coded. These letters generally indicate the type of insulation or its environmental rating. The types of conductor insulation described in this module include those shown at the top of NEC Table 310.16. Various insulation codes designations are shown in Table 2. So B is abrade, E is ethylene or entrance, F is fluorinated or feeder, H is heat rated or flame retardant. When you have two of them, it's high heat, it's 90 degrees Celsius. 1H is 75 degrees Celsius. N is a nylon jacket, P is propylene, R is that rubber, that was that thermoset. S is silicone, T is thermoplastic. That's the one you're going to see most often. We use a lot of THHN and THWN. U is underground. W is weather rated. That's a highlight. X is cross-linked polyethylene. Z is modified ethylene, tetrafluoroethylene. You don't need to memorize that. TW is thermoplastic weather rated. W is weather rated. T is the thermoplastic. FEP is fluorinated ethylene propylene. FEPB has a glass braid. Mineral insulated MI. Moisture, heat, and oil resistant thermoplastic. So the T is the thermoplastic. The W is actually the moisture. And the M is the heat, I think. MTW, mineral. PFA is, I'm not going to read that. RHH, so this one we know is rubber and it's high heat, so it's good for 90 degrees Celsius. It's got high heat, HH. And rubber is that thermoset, that rubber. This one is good for 75 degrees Celsius, and it's also rated for wet location, weather rated. So it's a rubber, it's heat rated, it's weather rated. All right. You'll catch on the more you use this. T is thermoplastic, high heat, that's 90 degrees Celsius, and N is a nylon jacket. This one's thermoplastic, high heat, but it's also weather, moisture resistant, moisture rated. This one's only good for 75 degrees Celsius, THW. THWN, that has a nylon cover on the outside of it. Underground feeder, UF. Underground service entrance, USE.